Okay, now that we've defined independence, I want to do an interesting coin tossing exercise. At least I think it's interesting. Okay, so what's the deal? The deal is we're going to assume we have a coin that has a probability of P of landing heads. So suppose we have a P coin. So a P coin is a coin that has probability P of landing heads. All right. And let's define Q as 1 minus P. Q is going to be defined as 1 minus P is the probability of tails. We're going to flip the coin n times. And we're going to do that independently. We're going to count the number of heads. In those n tosses. Okay. What is the probability? This will turn out to be a pretty important distribution that we'll talk about later called the binomial distribution. But what is the probability of having k heads? It's something we can do without that. What's the probability of observing k heads in those n tosses? We should be able to do this now. Okay, let's think. We've got n tosses and we want to have k heads. We don't care what order, we just want k. Okay, so how do we do this? Well, we've got independence, which is nice. Let's just say 1, 2, 3, 4, etc. N. So we want k heads, and we can put them wherever we want. Okay, so we can put the heads in any of the k spots. So we can pick whichever spot we want out of the n. So there are n choose k possible arrangements. And regardless of the arrangement, the probabilities are the same because of independence. So among the k heads, each one had a p probability of coming up heads, and they're all independent. So by the multiplication rule, it's just p times p times p times p, k times. That's p to the power k. Similar logic applies to tails. So each one had a probability of coming up. There's n minus k left. Each one had a probability of coming up tails. Q times Q times Q times Q times Q, etc. N minus k times. Okay. So now what we're interested in calculating, we're interested in trying to figure out what's the probability of what is the probability of an even number of heads in n tosses. Well, we know that even number of heads, it's just going to be the probability that you are 0, 2, 4, 6, etc. up to the lowest even integer less than n. Well, those are mutually exclusive, and we know the probability of each one, which we calculated up above right here. So it's really just the sum over all even values of k, of n choose k, of p to the k, q to the n minus k. Let's define that as p sub e. That's the probability of an even integer. And similarly, let's define p sub o as the probability of an odd number of heads. So we know that's the complementary probability. We know that p sub o equals 1 minus p sub e. And because of that, we can say p sub e plus p sub o equals 1. Okay, so that's our first observation. We want to get a closed form expression for the probability of an even draw. Okay, how are we going to do it? Okay, well, let's think about it. Is what we want to end up with is we're going to get an expression of two probabilities and two unknowns. Okay, this is true, but it doesn't tell us anything about what the value of PE is. Right. So now let's think about, okay, what's the probability? What's the value of P minus PO? Well, in this case, for the even terms, we get a positive. For the odd terms, we get a negative. Right? So notice that for the even terms, we get a positive. For the odd terms, we get a negative. So we can write this as sum of k equals 0 to n. The negative term can just get folded into the p, because when the number k is even, -1 to an even power is just +1, and we get a positive term. When it's odd, we get a negative term. So this actually turns out to be n choose k minus p to the k, q to the n minus k. Now we use the binomial formula. We've seen in one of the first lectures that this expression, where these binomial coefficients come from, is, just to recall, x plus y to the n is the sum from j equals 1 to n choose j, x to the j, y to the n minus j. So what do we have here is we actually have an expression which is we actually have an expression which is in terms of minus P and Q. Right, so this is equal to, by the binomial formula, Q minus P to the power N. Okay. So what does that tell us? Well, PO is 1 minus PE. So this is PE minus 1 minus PE. Simplifies to 2 times PE minus 1, which we've just calculated as Q minus P to the power N. So rearranging tells us what? It tells us that the probability that P is even is 1 plus Q minus P to the power N divided by 2. So pretty interesting to get a very closed form solution in this case using a little bit of a algebraic technique. And we can check our intuition by saying, okay, suppose that Q and P are equal. That happens when P is a half. Then this term goes away. Here, this Q minus P to the N, and we're left with 0. We have 1 plus 0 over 2. So the probability of even is a half, probability of odd is a half. I don't know if I would call that intuitive, because I don't know if I would call that intuitive or not. I'd have to check there. It sounds intuitive at first, but it actually is pretty surprising on the other hand. So I'd have to think more about where the intuition comes from there. Maybe it's obvious, but the last thing I want to do is just assume that something's obvious because it gives a nice answer of a half. To me, it's not obvious. So I think that's pretty interesting. Okay, so I think that was a pretty, I think that's pretty interesting coin tossing exercise where we're able to use the binomial theorem in a pretty creative way to calculate a probability that at first looks pretty difficult to deal with because we have a sum over even integers. And if you tried to do this yourself in a more brute force way, I think you'd have some difficulty. So this is a pretty clean and nice way to be able to do it.